Okay, high linear algebra. So this is a screencast that picks up what we talked about in class, and it's also part of your homework given today, Monday the 18th, and it will be due on the 20th on Wednesday. Okay, so I want to talk about two-dimensional linear transformations. Okay, and because we're staying in two dimensions right here, I'm saying specifically that this is a transformation that maps a vector in R2 to a vector in R2. Okay, we're staying in two dimensions here. Okay, if this was a vector in R2 being mapped to a vector in R3, it could still be a linear transformation, but it would not be restricted to two dimensions. So here is why I specify two-dimensional linear transformations. I also want to say to you too, full disclosure, I am going into a great deal more detail than your text does. One, because I think it's important, and two, because I think it will lend just more heft and meaning to the next section in your text. That, truth be told, I think it kind of, the next section 1.8, it goes into that section very superficially, and quite frankly, I think that you can handle more. Okay, so that's why I'm doing this. So what I'm going to do here is, and you know what, full disclosure, I'm a big believer in footnoting and sourcing and that kind of thing. When I was thinking about this example, I wanted to find an example that I knew was not going to get me mired in any kind of mess. So I just Googled, I just said, like, not Googled, is it called Googling? Or I searched, I guess, right. I just searched for numbers that will work out really well. And I happened upon, interestingly, one of these casts by Khan Academy, which I think is okay. I actually think they do a legitimately good job. I think that this example that they pulled, that I pulled this example from one of theirs, I don't think that their explanation was entirely thorough. I mean, I wasn't a big fan. But it just proves that point proves to me, at least, that I don't know that people out there, including Mr. Khan, who did the video that I saw, I don't know that he fully actually understood what he was doing. But oh well, I guess we'll know more than him. All right, so here's how I want to start with this example. Okay, let's say that I'm telling you there is some transformation T that maps the vector 1, 1 to 4, -2. Okay, I don't know what that transformation is. I mean, maybe you would look at this and say, oh, I know what the transformation is. The x component is multiplied by 4 and the y component is multiplied by -2. I mean, that's one way to have gotten there, but we don't know that. I mean, maybe, the x component is, I don't know, like 2 times the y component plus 2, for example. And maybe the y component is -2 times the exponent. In other words, if I asked you to find a relationship between 1 and 4 and 1 and -2, okay, 1 and or 1 with 4 and or -2, there are infinite possibilities that you can come up with just given this relationship. I mean, I could say, oh, I know what the relationship is. The transformation takes the x coordinate and adds the x coordinate plus 3 times the y coordinate to get the new x coordinate, and the y coordinate is a result of, oh, I don't know, -2 times the x coordinate plus 0 times the y coordinate. The point I'm making is that just given this information alone here, you don't know exactly what that transformation is. And remember, the word transformation is replacing the word function that we've used, okay? So I need some more information. I'm going to give you some more information. I am going to say that since we know, okay, the vector 1, 1 is a result of 1, 0 and 0, 1, okay, and these right here are the standard basis vectors I and j, okay. I would like to know this. I want to know more specifically what does I undergo as part of this transformation? And what does J undergo as part of this transformation? And I have to tell you, I'm a little bit embarrassed. I made a screencast for my BC Part 1 class on, was it Friday? And I was doing it in my office while I was having a full-on conversation with Miss Ament and like a bunch of people coming in and out of the office. And I think I was kind of showing off, in all honesty. Now that I think about it, I think I was just showing off. Anyway, I got so caught up in me showing off that I made so many rightos and speakos in my screencast that I'm a little embarrassed. So I'm a little embarrassed. Okay. But anyway, so I'm not doing that now. So here's the question. So I'm told this very general statement, and my question is, I see this transformation here, but I'd like to break down this transformation some more. I'd like you to give me some more of the minute building blocks. And specifically, within this transformation, I would like to know the following. What happens, what is the transformation's effect on this unit vector I? And what is the transformation's effect on this unit vector J that will result in the transformation of the vector 1, 1 to that being 4, negative 2, okay? And that question, when I ask that question, an answer has to be given to me. If there is no answer provided, then you cannot figure this out, okay? So when I ask this question, I'm going to be told this transformation, okay? So here's the answer to this one. The answer to this question is the transformation, when I apply that transformation to I, the result is 1, negative 2. Okay? And when I apply this transformation to the vector, when I apply this transformation to the vector 0, 1, the effect of this transformation on the vector J is 3, 0. Okay? Now, this information is extremely valuable because, remember, the number 1, air quotes, in two-dimensional vector space is I and it's J. And if I can say, I see the transformation that is being applied to the vector 1, 1, but for me to know what the general transformative rule is, I would like to know how that transformation affects the number 1 and the number 1. Because if I know how the transformation affects the number 1, I can then generate a rule. Follow me this way. If I know in one space, in R1, in one-dimensional space, that there's a transformation that takes the number 1, and when I multiply the number 1 by 4 and add 2, I get 6. So if I say to someone, if we say that that number 1 in one-dimensional space becomes 6, okay, by multiplying it times 4 and then adding something, you can figure out the rule. Oh, it's 4x plus 2, okay? So when I look here, this tells me that, interesting, if I am taking the matrix 1, 0, and 1, 0 becomes 1, negative 2, I'm looking here for a relationship between 1, 0 and 1, negative 2. I can do this here because this is the number 1. This is not the number 1. And if I look at this here, what I see is the following. 1, 0 equals 1, negative 2. In other words, the transformation from 1, 0 equals x coordinate stays the same, y coordinate is negative 2 times the x coordinate. So in general, I have determined this. I have figured out the rule that if I have some factor of 1, 0, look at this, x comma 0, right? x0 is just x times the length of 1, 0. The result here is going to be x negative 2x, okay? This is x here, just a multiple of 1, 0. How about this? Well, if I look at this, the transformation from 0 to 0, 1 results in 3, 0. This tells me that in general, if I take a scalar multiple of 0, comma 1, I'll just call it 0, comma y, right? The result is going to be, what do you think it's going to be? Yes, very good, 3y and 0, okay? Once again, what looking at 1, 0 and 0, 1 allows me to do is figure out the general rule for vectors that would be scalar multiples of the number 1 in air quotes, the vector I and the vector j. Do you understand? Okay, well, what would then, here is the question. The question we want, the question we are trying to answer is, what then is the transformation, right, that maps any vector x, y, okay? Well, let's see. Let's break it down. Since we know that vector xy equals x comma 0 plus 0 comma y, right? Or alternatively, in column vector form, Tyler, what are you doing? What show? Okay, what does basically watching something mean? Does that mean yes, but you just don't want to say yes because mom's gonna yell? Okay, so you're watching something. Oh my gosh, I didn't even pause this. Okay, never mind. Okay, so then the question here is, okay, now what did I just leave off? Oh, yes. So what then is the transformation that I could apply to any vector xy? Okay, well, let's see. Since xy is the result of x comma 0 plus 0 comma y, it would make sense then that the transformation okay, let me write it down first. Okay, this is going to equal the transformation that I could then apply to the vector xy. Well, let's see. What is the transformation that you could apply to x0? This is x negative 2x. What is the transformation that one could apply to the vector 0y? It is 3y 0. That means, look what I found. I have found that the transformation that I could apply to any vector that would yield the relationship from up here is the following. Oh no. Is this x plus 3y negative 2x. Okay, let's check. Let's just check. Let's check. What if I use this transformation and apply it to the vector 1, 1? Let's see. If I apply 1, 1 to this, if I apply the transformation to this vector 1, 1, the result is going to be, let's see, 1 plus it is 4, negative 2. There you go. Ding, 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 ding. Okay. With this transformation, I can now ask you a bunch of follow-up questions. I could say this. What then would the image of 615b under this transformation. Sometimes the word image is used. Could you kind of figure out why? The reason why is because when you talk about a transformation, I mean, here's where you can get a little bit. I mean, you can get a little bit deep and touchy-feely if you want to. When you transform something, I mean, this is not necessarily a mathematical idea. When you transform something, you take one thing and change it into another. Okay, that which it changes into is oftentimes called the image. All right. So what then would the image of the vector 615 be under this transformation? Well, under this rule, the transformation of the vector 615 would be, let's see, 6 plus 15 times 3, 45 plus 6, this is 51, and negative 12. Okay? Now, I want you to think about this. Now I want you to think about this a little bit more abstractly. Okay? What's happening here is some two-dimensional entity, a vector, whoa, that's a wild idea, a vector is being transformed into another two-dimensional vector, okay? Back in our kind of one-dimensional mathematical state, when I had something like f of x equals 3x minus 7, we were relatively unimpressed because I would say, what's the transformation of 3? And you would say 3, the transformation of 3 is it becomes 2. Actually, you know what? In one space, this notation seems a little bit weird to me, but you'd probably use this, actually. Maybe you'd use this. Anyway, okay. The point is that this doesn't really excite you. I don't believe that any of you are going to look at this and say, oh my gosh, there's some transformation that takes the number 3 and it changes it into 2. That transformation is a linear transformation, okay? What happened here, and this is sometimes you'll see it right this way, what happens here is that 3 is transformed into the function 3. Right, that's what happens. Or more generally, you may see it written this way, like the transformation t takes that x and it transforms it into 3x minus 7. Sometimes you see that. When you write it this way, it says like, this is what I input into this operator and I get to. Anyway, the point is that I don't know that this excites you. Like, I don't think that you say to yourself, oh my gosh, if I plug in 6, I get 11. Whoa, the number 6 is transformed into the number 11. Like, my guess is I don't think any of you are jumping to your Snap tweets or do anything like that and saying that was mind-blowing. This is a little bit odd. But if you say to yourself, wait, how can one vector become another vector? Well, I'm going to say back to you, well, how did one number become another number? There was some transformation here. There was some transformation here. And in this case, the transformation was right here. Okay, and what I'm going to do is pick up precisely with this example when I see you on Wednesday. But right now, what I'd like you to just take stock of is what I just wrote about and talked about. You know, the way when we were given one transformation's pre-image and image, how these more detailed questions and this information here allowed us to generate the general transformative rule, okay? But I'll pick up right from here when I see you next. So there's no homework associated with this, but I just wanted to make sure I gave this to you, and I want you to, I guess part of your homework is to, after you listen to the screencast, like really listen and digest it, and, you know, have a reaction, have an emotional reaction. What did you think? Was this mind-blowing? Like, I don't know. Okay. And then we'll talk later. Okay, bye, linear algebra.